All right, so today we are going to finish off chapter 24. Okay, we just got a couple of reactions. I am still kind of trying to figure out exactly what we're going to do with the rest of this week and one day next week. Cancel it. No, you got to get your full money's worth, right? All right, chapter 20. Okay, let's quiet down. Chapter 25 is on means. And I remember in our old textbook, so just that we were using it, I guess it was still the year before last, for the last time that I taught this course. The chapter on the amines didn't really have that much chemistry in it that was, I think, super useful to us at that point. And so I usually just kind of like dip through that thing and then move on to some of the biological chemistry. But there's a lot more chemistry in this amine chapter. Some chemistry that used to be in other chapters earlier on that we used to always cover. So I guess I'm trying to decide whether to more fully, not maybe do all of it, but more fully do chapter 24. And because we don't have much time to really survey a lot of biological chemistry. But I'm still in a quandary there. All right. So, we have been looking at reactions in this chapter that use the carbonyl compounds both as the electrophile, which is the first way we learned to use carbonyl compounds, and as the nucleophile. Okay, so they're playing both roles in this little play. And we've looked at essentially two reactions for that. The first one was the aldol reaction, remember, which was usually the reaction between either aldehydes or ketones. And then on Friday we looked at the Claisen reaction, which is the reaction between two esters. Okay? The aldol reaction would at least initially give a beta hydroxy. So hydroxy is an alcohol, right? Hydroxy aldehyde or ketone, depending on what we started with. And the Claisen gives us a beta keto ester. Okay? So we're going to just look at we're going to look at one more reaction here. It's called the Michael reaction. And the main difference here is that the electrophile is an alpha beta unsaturated carbonyl. Meaning that we're going to add in a situation where we can do conjugate addition to a carbonyl. Okay? And then the Robinson annulation is just kind of an interesting combination of all of this stuff. And it's a ring-forming reaction, which an annulation is, but it combines both the Michael reaction, so the addition to an alpha-beta unsaturated carbonyl, and an intramolecular aldol reaction. Okay, so it has a lot of different steps in it. So we'll take a quick look at both of those. Then we'll probably practice. I tried to come up with a few synthesis examples, and that's what we'll do today. Okay, and then by Wednesday, I will have figured out what we're going to do on Wednesday, and I'll post some notes, and so you guys will have those before, hopefully by tomorrow afternoon. Okay? Any questions? All right, let's do a clicker. All right, so mind ourselves first. So here's the Michael reaction with alpha beta unsaturated carbonyls. Okay? So remember, because these types of, here I'll just draw it down here, because these types of molecules have several different resonance forms, so we could draw one resonance where the pi bond of the carbonyl just moves up onto the oxygen. Right? That would give us a resonance structure that looks like this, with a plus on the carbonyl carbon. This resonance just kind of reinforces that we have a polar bond in this carbonyl, right? We have a delta minus on the oxygen, delta plus on the carbonyl carbon. It's that delta plus which was the driving factor for all of the chemistry we learned in the beginning, as the carbonyls acting as electrophiles. Okay, but when we add that double bond, it gives us another resonance structure. So if we essentially just ignore this oxygen right now, we see that we have an atom with a plus next to a pi bond, and so we can draw another resonance form which moves these electrons over here. And we have some plus charge out on the terminal, or the beta position, right? This is here's the alpha position, this is the beta position. Okay? So when a nucleophile reacts with an alpha beta unsaturated carbonyl, there's two possible places that it can react. Right? One is to react directly at the carbonyl carbon, chemistry that we saw the most of. The other possibility is for it to react with the beta position. All right? What we said before was that if this nucleophile, if it's very basic, then it usually adds at the carbonyl carbon. So this would be a 1-2 addition. All right? That's where the most delta plus is. And so the nucleophile is drawn to that position more strongly. If the nucleophile is weakly basic, then we can get a 1-4 addition. Okay, this product turns out to be more stable, and so we get this under thermodynamic conditions where the reaction becomes reversible. And it becomes reversible because if that nucleophile is a weaker base, then it can act as a leaving group, and the reaction can go backwards too. All right, so it can equilibrate, and it can go to the 1-4 addition. Right? We saw that reactants, like, Grignards, and probably alkyl lithiums and hydride, so sodium borohydride or lithium aluminum hydride, these all tend to do 1-2 additions. The weakly basic ones could be things like, I think that we showed examples of just using something like HBr, so it in fact protonates first on the oxygen, and then the bromide is a weakly basic nucleophile, can do 1-4 addition. I think some of the sulfur nucleophiles can do that. And cyanide is another one that can do it, but the main kind of prototype nucleophile for doing this are the organolithiums. Okay, that's kind of what their main thing is. To like this, copper, lithium. All right, so those are the kind of groups that can do 1,4 additions. Okay, so what we're going to do here is we're just going to add a new nucleophile to this 1,4 addition. Okay, and the nucleophile is going to be an enolate. All right, the most weakly basic enolates are the ones where we've deprotonated and that enolate is conjugated to 2 different carbonyls. All right, when we get to doing the Robinson annulation, I'll show some of those examples are not between 2 carbonyls, but these are kind of some of the best ones. And so what happens is that this is going to come over here to the beta position, and we'll go to the, we'll draw this out. Let's see, I'm going to draw it down like this. Okay, so I'm going to attach this whole group here. OCH3, oops, carbonyl OCH3. So this whole malonic ester attached to the beta position, right? And the electrons go to the alpha position, so we've essentially generated an enolate right here. Right? So to get to our product, then we just have to protonate this. Right? So we can use, I don't know if I can fit this all in here. Just use our methanol, or we might have to add some dilute acid because, well, this isn't conjugate, well, no, this is probably okay. All right, and so then, wow, how am I going to do this? Okay, so here's this. Oh, maybe it's not as bad as I thought. I'll just do CH2 to CH3, CO2 CH3. Okay, so we've just added this malonic ester to the beta position of the alpha-beta unsaturated ketone. All right, we can do the same kind of thing. This is acetoacetate down here, right? We talked about the acetoacetate synthesis. If we generate, so what kind of base would we use for this one? Right, so we usually use the base that matches the ester, right? So we've got ethoxide in ethanol. Right, I won't show the deprotonation step because we just don't have enough room, but we make the enolate at the most acidic position here. This attacks at the beta position, forms that enolate, and I'm just gonna do these in both, all in one step this time. So this is gonna add the kind of the H plus, and so we would get this acetoacetate attached at the beta position. Like that. Okay? So it's just another example of a reaction we saw before, but this one specifically called the Michael addition. Okay, everybody follow that all right? Now let's look at this one. This is called, this is the Robinson annulation. Okay, so it's going to take 2 pieces. We're going to have an alpha-beta unsaturated ketone and another ketone. Okay, and when these react, just in hydroxide, let's just draw out what the product is. Okay, so it's going to be a ring-forming reaction, an annulation. And so we are going to get this molecule right here. So let's see if we can find the pieces. All right, so this ketone here, that oxygen is going to be gone. That part goes right here. Okay? And the alpha beta unsaturated ketone here is going to go right here. All right, so here's how it works. First step is going to be to deprotonate this ketone, the one that's not the alpha beta unsaturated one. So this is going to deprotonate this, and we're going to form an enolate. So here's our anion right here. That now reacts with the alpha beta unsaturated carbonyl, and it does a 1,4 addition. Okay, so we're going to go down this way, and I'm going to draw this like this. And so this is going to attack here, and we'll draw the enolate that forms as the intermediate in that reaction. Okay. So we've at least attached these two pieces now. Okay, so if we look ahead, what do you think we need to have happen? Do we want that enolate to react with a ketone or anything? No, because that would form a 4-membered ring. So what we really need is we need the enolate on this side. Okay, because then if this enolate, if we form an enolate here and it reacts with this ketone, we have an intramolecular aldol reaction that forms a 6-membered ring. Okay, so we have to just go through 2 steps of some acid-base chemistry. We need to protonate on this enolate. And then we're going to deprotonate on the other side. Okay, like this, and then I'm going to draw an extra H in there. So the next step is our hydroxide, and that's going to deprotonate on this side. And I'm not exactly sure why every one of these steps happen. You know, really this should all be probably in equilibrium. But you can get to the final product, so at least this is a way to rationalize how it can happen. Let's see, so this is the ketone here now, and now this, I'll just draw it like this, this is the enolate, this is the anion on this side. Okay, so now we essentially do just this intramolecular aldol, so this can attack here, 6-membered ring, these electrons go up on the oxygen. I'm going to make these kind of small so we can still get there. Okay, we have a ketone. We've made the ring now. And we have an O minus. Okay, so now look at the product and look at where we're at. What do we have to do? right? We need to essentially get rid of, we want to protonate here and then do a dehydration, right? Remember that was a step that we could go to when we were doing the aldol. So we need to protonate. Let's do it on the other side. Let's use our water. Now we have an OH at that position. And remember, in this dehydration in basic conditions, it followed this other mechanism. It was called the E1CB, right? So it's an elimination, but it goes through a conjugate base. And so that conjugate base is formed by deprotonating at the alpha position. Okay, we got just one more intermediate here. This is going to pull off the alpha proton and form an enolate right here. And then by adding that extra electron density to the alpha position, it can push off the hydroxide. All right, oops, I need a minus charge here. This is kind of crowded as usual, huh? All right, so that goes here, and the hydroxide comes off. And it forms our double bond. Okay, so there's two parts to this, right? The first part, to get to here, right? The first half is the Michael addition. Okay, because in that reaction we do the 1,4 addition, we protonate to get our product. Okay, so this part, let's go to here. This is the Michael, or the Michael reaction, I guess they call it. Reaction. And from here, around here, this is an intramolecular aldol, followed by the dehydration. All right. So how do you think they figured this out? Do you think they planned it all out in advance, or they just mixed some stuff up and they were like, "Whoa, look, we got some product and we got to figure out what it is"? I think it was probably more like the second one. And back when they discovered this reaction, a lot of these reactions, they didn't even have techniques like NMR or IR and stuff. They had a really hard time to try to figure out what these molecules were. Yeah.
So obviously this mechanism is very complex. How do they know it goes through these specific steps?
Right, good question. So the question is, how do they know they go through these? I don't know exactly for this reaction what studies they've done, but, sometimes what you could locate at least what pieces go where, right? For one thing, you could just do different analogs, right? If you add another methyl group here or another methyl group over here, you can see where those end up, right? You could put things like deuterium instead of hydrogen, and see where they end up and things like that. Yeah. All right? So, pretty cool. So, how would we make these compounds using a Robinson annulation? All right, 2 of them only have a single ring, but the way that we can figure out where, notice that we're starting with an alpha beta unsaturated ketone, but we're also making an alpha beta unsaturated ketone, right? And so the double bond of our product alpha beta unsaturated ketone is where the dehydration took place. Okay, so we could just say, well, let's just draw a few intermediates here on the going backwards, and we can figure out what pieces we started with. Okay, so we got this. Where would the alcohol go for our dehydration? Okay, remember that the compound that dehydrates is the product of an intramolecular aldol. So what kind of a molecule do we get as a product for an aldol? It's the beta hydroxyketone, right? So the alcohol is going to be at the beta position of that ketone. Okay, and we're going to get to there by forming this bond. Like this. Okay, so this is just basically one, like one of the intramolecular aldols that we probably drew the other day, right? So we would form an enolate on the methyl, and it would attack the carbonyl to give that alcohol. And then this, we're going to form from an alpha-beta unsaturated ketone, so it's going to break right here. And it would go to this plus this. Okay, so the first part would be an enolate from here, doing the alpha-beta unsaturated carbonyl, adding to that alpha-beta unsaturated carbonyl. And the second cyclization is going to be an enolate from this position, attacking this ketone. All right, so whenever we look at one of these, we can say, oh, we're going to break this position. This is going to become a ketone, and the enolate from that is going to form that bond. Okay? So, try to take those same disconnections on the next one and see what two pieces you'd come up with. Okay, you don't have to go through every step if you don't want to. All right, so we're going to draw the same lines we did up above. So we're going to break this bond, and we're going to break this bond. Okay, so we're going to disconnect those two pieces. And this is the phenyl ring, like this. This part is going to be the alpha-beta unsaturated one, just like up above. And this is going to be ketone. Right? So the first addition is the Michael addition on this side. Right? It gets protonated, reforms an enolate over here, and that attacks the ketone on that side. All right, we could do the same thing at the bottom. We see where the double bond is here. We're going to break that one. And then we can kind of count from this position, go one more over, and then we're going to break that one. So, benzene doesn't really break here, but we have this. With a ketone there, and alpha beta unsaturated ketone here. Okay, so the way it combines, an enolate from this side does the Michael addition, right? An enolate from this side does the intramolecular aldol, followed by the dehydration to form this double bond. All right, through all those steps we drew out. Okay? All right, so that's the last reaction that we're going to really look at. What do I have? Oh, this is just saying what we've done, but we need to do some synthesis now, really, to have fun. Let's see, what did I think up here? All right, I'm going to add a new slide in here. Okay, so the first one, what we're going to do is we're just going to start from this alcohol, and we want to convert that into, oops, what happened? This alcohol. So just take a moment here. That should be all it would take you, right? Yeah, done already. And think about how you might at least break this apart, how we would do this.
I say just throw PCC at it.
Huh?
Just throw some PCC at it.
Yeah.
No?
Okay, what if we say that essentially the last bond, at least for making the carbon chain, would be to make this bond right here. Okay, and so then I'm going to draw this. Like this. Okay, so how would we make this compound? An aldol reaction, right? Because that would be forming this bond right here, then enolate going to the aldehyde. And so this essentially just is the combination of two, right? So this is the aldol, and then how do we get from here to here? PCC. Yeah, PCC would be fine. Okay, so there's another little trick to this though. Okay, so we can start with this aldehyde, PCC, we get the aldehyde, alcohol to the aldehyde, and then we can just use, for this dimerization, we can just use hydroxide and water, the basic conditions like they do in the examples. So we get to this is the aldol product right here. So what about getting from that aldol product to our final product up above? Can we just do a Wittig reaction? Right, so we have to, because the Wittig is basic, we can't do that in the presence of the alcohol. So we have to protect the alcohol first, do the Wittig, then deprotect it. Right, so how do we protect an alcohol? As a silyl ether, right, is the common way. So I'm just going to do chlorine, silicon with 3 R groups, and we usually add in some imidazole. Here's imidazole. Okay, so that would form O. Remember that this is an ether now. It's a silyl ether, so we want to draw that oxygen in there. Okay? Then, I'm going to have to do 2 steps here. Then we can do our Wittig. We just want to add 1 carbon, right? So our ylid would just be like this. Okay, so that would do the Wittig, and then we could deprotect. So what do we use to deprotect the silyl ether? Yeah, fluoride anion. So they oftentimes use this tetrabutyl ammonium fluoride. Okay? All right, which other one should I do here? Everybody with me? You guys get that one? Let's do a trickier one here. Oh, I gotta add a new, where do I add that? I take a reaction from last semester. So you're gonna have to dredge something up here. We're gonna go from there, I don't know if we'll have full time to do this, to here. What the? What? All right, let's start backwards. How might we make that product? Yeah, we just did all those reactions, right? So we could make that from an intramolecular aldol reaction from this diketone. Okay, so the enolate here. Remember, when we do these intramolecular aldols, it's going to want to form the most stable ring size that it can, right? So the biggest ring that this one, if it deprotonated the alpha position here, then that would form a 3-membered ring, right? So if we deprotonate on the methyl group, then we can attack here, gives the alcohol, dehydrates, gives us our 5-membered ring. Is this really? Oh, I messed up though. Dang, that doesn't even work. 1, 2, 3, 4, 5. Let's we're gonna run out of time. Let's add 1 more carbon in here. Good thing it's not in the middle of the exam. Okay, like this. We're going for the 6-membered ring this time. So now there's probably going to be different ways, but still isn't what I thought I was doing here. Okay, here's what I had in mind. We were going to go through this. And then, to form a diketone, we are going to cleave this bond right here. Anybody remember how to do that? That's the ozonolysis reaction. So let's see if we can actually come up with a product that I meant to have here. Oh, that's what I did wrong. Oh yeah, dang. If I would just draw what I actually have on my paper. there. Oh. Okay, so we get to here. So this is ozone followed by dimethyl sulfide. Give the diketone. Then we do an intramolecular aldol, which in this case it's going to want to go from here to form a 1, 2, 3, 4, a 5-membered ring. Oh, let's do it let's do it the other way. From up here to attack here. And so then we're going to have this and this, and that dehydrates to go up there. Okay, so then the key, which we don't really have time to now, but you guys ought to be able to do this. We did a similar example as this, is to go from this ketone to give us this dimethyl alkene. All right? So dredge up what we did before, see if you can do that part. Okay, so I will see you guys on Wednesday. Look for some new notes for Wednesday sometime tomorrow, late tomorrow afternoon probably.